Hi, in this video I will present software developed as part of my ongoing master's thesis under the supervision of my advisor Dr. Chris White. This framework explores how sensory memory and short-term memory influence music cognition with a particular focus on evolving tonic recognition. By integrating real-time tools with user-defined memory adjustments, it offers an approach to analyzing memory durations and their effects on tonic perception. First, I will demonstrate the end result of the software and explain how it works. Then, I will present computational mechanisms underlying the system. This software idea stems from the need to visualize the thought experiment described in my master's thesis. How would a hypothetical person with a memory duration capacity varying from 2 to 8 seconds assign tonic perception to this chord progression? The system bridges computational backend processes with digital audio tools utilizing MaxMSP Ableton Live End protocols such as MIDI and OSC. Its workflow seamlessly synchronizes user-defined memory parameters with live or pre-recorded musical inputs. The platform's interactive interface enables dynamic adjustments, facilitating applications in live performance, corpus studies, and education. This study advances the understanding of memory's role in music cognition and positions the system as a tool for academic research, music theory and musicology, and assistive technology development. This is the flowchart of the system, which begins by defining three types of signals: Audio signals as raw audio from instruments, MIDI signals, encoded musical data used for precise musical interaction, info signals are metadata such as tempo, sensory memory, and short-term memory updates. Musical instruments produce MIDI or audio signals that initiate the data flow in the system. MaxMSP handles audio to MIDI conversion, bridging audio signals and digital workflows. Converted MIDI messages are forwarded to Python through OSC or User Datagram Protocol (UDP) for further processing. Ableton Live integrates into the system for real-time MIDI output and metronome synchronization. The metronome state is toggled using OSC commands such as turn it on when click taken variable is updated. The MIDI library in Python captures and processes MIDI data for memory analysis. For example, it listen to MIDI function in base.py uses MIDI library to capture not-on messages, extract pitch classes, and update the sensor memory capacity container. The OSC protocol is essential for real-time communication between Python and external tools like Ableton Live. Python's sendState-to-WebSocket function transmits updated system states to WebSocket clients using OSC. The Python backend is the computational core handling real-time updates, memory management, and data transmission. As key functions, sendState-to-WebSocket updates and transmits system states to clients, manage sensor memory capacity, dynamically clears and updates sensor memory, handle metronome state, synchronizes the metronome with user inputs and system tempo. As an example workflow, user input adjusts the tempo, Python recalculates sensor memory and updates clients using WebSocket communication. The HTML interface allows users to interact with the system by adjusting parameters and visualizing memory states. As key features, input fields for parameters like tempo and memory capacity, real-time visualization of sensory memory and short-term memory states. Users submit tempo values through the interface, triggering the sendTempo function in script.js to update the backend and display changes. JavaScript manages front-end logic, ensuring real-time updates and synchronization with the backend. As key functions in script.js, sendTempo function sends updated tempo to the backend via WebSocket. Update key function determines and displays the current musical key based on memory contents. Reset and refill STM container clears and refills the short-term memory container dynamically. The WebSocket server server.js broadcasts updates across connected clients, ensuring real-time synchronization between all components. As an example workflow, a musician plays a note generating a MIDI signal. Python captures the note-on event and updates the sensory memory capacity. The updated state is transmitted to WebSocket server. JavaScript processes this state and updates the HTML interface, displaying memory contents and the current musical key. In conclusion, this system represents a seamless integration of hardware, computational processing, and user interaction, enabling dynamic memory analysis in music cognition. Its modular workflow supports real-time experimentation and educational applications.